So we're gonna be going over linear momentum again, because I think we started it a little bit last class, but I'll just give a quick review. So momentum is the quantity of motion an object possesses. Momentum is P equals mv. P is the variable we use for momentum. Uh, yeah, so it only depends on mass and velocity because the equation is just mass and velocity. Momentum has direction, and a heavy or fast object has more momentum because of the mass and velocity. Those are the only two things that are taken into account when finding momentum. Okay, yeah, this is an example. A 5 kilogram bowling ball moving at 3 meters per second has 15 kilograms meters per second of momentum, and this is 5 times 3 because 5 kilograms is mass and 3 meters per second is velocity. Does that make sense? You can just give a thumbs up if you guys get that. Yeah, okay. So impulse. Impulse measures how much force it takes to change an object's momentum. And so impulse is this force times change in time. Uh, Impulse momentum theorem. Just impulse is equal to change in momentum. Um, so that's what impulse is. And it's taking impulse is used in the design of airbags, seatbelts, and all these things because as an airbag works, pretty much is I can try an example here. You have a person here, and they have momentum going forward here, but an airbag expands, and as the guy, oh, hello, Sanchana, as the guy goes forward, he presses his face against the airbag here, right? And what this does is this increases the amount of time your face and the airbag is in contact with each other. So that increases the time here. So that means the force will decrease. You guys understand that? So these are imagine a multiplication symbol here. And this is a constant value here. So if the amount of time the two forces are acting increases, the force must decrease, the force at every instant in time. So pretty much you have less force over a longer period of time versus a lot of force in a very short period of time. It's still overall the same amount of impulse, but a seatbelt and airbags, they just make sure you don't die instantly from that super high level of force because it's increasing it over in a longer period of time. Yeah, Jane, could you summarize what we're doing right now in chat? We're not very far in. Um, so do you guys understand the concept of force times change in force times time in impulse? It's the same thing with a baseball. So a baseball has is traveling forward like this. It has when it comes into contact with something, it'll deliver a force to it. So if you wanted to catch a baseball right, if you wanted to stop it instantly, it would take a lot of force. But uh if you let your hand follow through with the baseball, you're doing less force over a longer period of time. So therefore it's less force at every instant, so it's easier. But just it's over a longer period of time. Do you guys get that? If your hand follows through with the baseball, it keeps contact with it the entire time, you need to have less force at every moment, which makes it easier. You guys get that? You can put a thumbs up or something. It's not, this is not an A here. This is a delta symbol. It means change. J is equal to force times change in time. Oh, okay. Oh, yeah. So airbags work because they increase time over which a collision occurs, and a longer time means a smaller force. Because remember, this formula is this. So if the time part of it goes up, the force part of it will go down. That's pretty much what this slide is about. Are there any questions? Okay, I'm gonna move on. Okay, now this is fun. Oops, this is fun stuff. So conservation of momentum. So in an isolated system, total momentum remains. Oh, I was going to say. In an isolated system, total momentum remains constant. the equation is total momentum before equals total momentum after. Or yeah, all the sum of all the momentum before is equal to the sum of all the momentum after. And requirements for this to be true, the conservation of momentum, is that there are I don't know what significant is here. I just ignore this word. No external forces and also a closed system. Okay, here's some examples of like pretty much closed systems, or like in like a physics class, and you have a question about this, you can assume these to be as closed systems. That's what significant is here, actually. So in two ice skaters, yeah, two ice skaters. I'm pretty bad at drawing, but imagine these guys. They're happy because they're demonstrating physics. They push each other apart. So one will go here, one will go here. Um, the total momentum before is going to equal the total momentum after. So since before they push each other, there's zero total momentum, and after they push each other, they're going in different directions. They must be going the momentum in this direction must equal the momentum in this direction. So P1 must equal P2. And these are in opposite directions. Can I slow down a little? Okay, yeah. Um, okay. So is there anything like you missed because I was talking too fast? Do you want me to go over anything again? Okay, I'm just gonna keep going. Just yeah, if you ever miss anything, you can just ask me to repeat it. Okay, yeah. Um, so rockets in space too. It's like the same idea. In pool ball collisions, it's the same idea. If you have pool balls here, there's and one here. This and say this guy's traveling towards these guys over here. Before the collision, there's gonna be some P initial momentum, and after the collision, it's gonna be the same, but just in like different like directions. Do you understand that? If there's no external forces like friction or like deformation during the collision, that's just conservation of momentum. So mass one, velocity one. Oops, I gotta add that knots. Mass one times velocity one knot. Uh, yeah, say this ball has a mass of one and a velocity of one initially. That's all the momentum in the system. And after, it's gonna have some after velocity prime mass. It's actually mass one is gonna stay the same. It's gonna have some prime velocity, some v prime for mass one, plus like all the different masses. Like say this is M2, M3. These are all gonna have a lot of velocity now. V2 prime. But like this equation will stay the same and you can like solve for it. So basically, as long as the system is closed and has no external forces, the momentum stays the same. That's correct. Yeah. I think you guys get this slide. Momentum staying the same also is like super helpful. Oopsies. If like they give you mass and velocity, because remember, momentum is just gonna equal mass times velocity. So pretty much mass times velocity before. Uh, if it's like of one object, mass times velocity of one object, it's gonna be, and say like a collision with another object is gonna equal mass one, two, seven. This is some new object M2 that it hits. It's also gonna give some velocity to it. So like this situation here, mass one, initial, okay. I didn't put initial here, but here. M1 times V initial one. So this is some object. Let's call this object one. It has a mass of M1 and it's going to be traveling at a speed of V1 before. And then after a collision occurs, it's still gonna have the same mass. This is object one. It's gonna have the same mass, but it's gonna have a new velocity. Like say it's in this direction because it hits a big mass over here, M2. And this M2 initially it had zero velocity, but now it has a new velocity. Say it's going in this direction with a velocity of V2 prime. Prime. If you ever see like this mark up here, it just means prime and it means like after an event. So I'll be using prime to say like after the collision. You guys all understand that? Like This is just momentum, but I'm using mass and velocity because we know momentum is composed of mass and velocity. It's the same thing as what China said. Like overall, this equation still means momentum before equals momentum after. Like technically I could add mass 2 here, but but the velocity of it would just be 0. So this entire term would just become 0, which is why I didn't include it. But if we're talking about the system as a total, mass 2 is in the system. It has no velocity, so I didn't include it. Do you guys understand that? Okay, nice. I'm gonna move on. Okay, so now stuff gets interesting. So there's two types of collisions, elastic versus, actually no, there's like, it's imagine like a spectrum. Elastic is on one end, elastic and inelastic, okay? Inelastic. And in real life, like collisions are going to be somewhere on the spectrum, depending on like the qualities of the material. But a perfectly elastic collision means momentum is completely conserved and kinetic energy is also completely conserved. We know momentum is always conserved in like a closed system. But what's important about an elastic collision is that kinetic energy is also conserved. Do you guys remember what kinetic energy is? 1/2 mv squared. You guys remember this is kinetic energy, 1/2 mv squared. You can put like a thumbs up. Mass, 1/2 mass times velocity squared is equal to kinetic energy. Okay, nice. Um, Kinetic energy is conserved in these types of collisions. And some examples of this are like billiard balls, and atomic collisions. And in these types of collisions, it'll be if it's two objects of the same mass hitting each other, say this object is going here and this object is standing still. If these objects have the same mass, what will happen is after the collision, this first ball will be standing still and the new ball will be going forward because the kinetic energy is conserved. And if these two have the same mass, the velocity is the only thing that will be carrying over in this collision. This is a perfectly elastic collision. So this ball comes over here, it hits this ball. This first, okay, I colored this. So the red ball comes and it hits the green ball, and these have the same mass. And after the collision, this red ball is now standing still, and the green ball is flying off with the same velocity the initial red ball had. That's an elastic collision. Yeah, like a Newton's cradle. The Newton's cradle has elastic collisions, I'm pretty sure. Yeah, that's correct. A Newton's cradle is an elastic collision. That's good. You guys know the like an application of it. That's a good example. And in an inelastic collision, momentum is conserved, which is momentum is always conserved in closed systems, but kinetic energy is not conserved, and this is the important part. So what this means is that like after in a completely inelastic collision, the two objects are going to stick together. So it'll be like, let me get the red ball. This red ball, this red ball is coming towards a green ball. These have the same mass, both mass m. But after the collision, the green ball and the red ball are now like together, moving as one object, but they're now moving with less speed because the mass is now, these are now considered as one like big M. I'll call this big M, which is this M plus M together. So now they have less velocity because momentum needs to stay the same, and momentum of this is just mv, lowercase mv. Weight, okay. Does this include magnets? Um, When like two magnets stick together, it's because like they're being held together. But I'm pretty sure in inelastic collision, it's just because like they're moving at the same speed. I don't know. Like they could be like many factors. I guess magnets could be an example of this. Well, yeah, magnets are an example. Say these two balls are magnetic to each other, and before this ball is moving towards a some set of speed, and after the collision, they stick together. They now have like a 2m combined mass, right? Because this is 2m, because each ball individually is m, and these are sticking together. So before, the momentum before was just mv, because it was only the red ball moving with a mass. Let's call this velocity v naught. And after the collision, it's now 2m v prime. So you guys can see that the mass doubled and the velocity changed. And if you just do like mass here, we can find v prime is equal to 1/2 of v initial. So the velocity was halved because the mass is now doubled. Examples are car crashes. The cars usually stick together, or like clay sticking together during a collision. It's just if any such reason, like the two objects stick together after the collision, it's a completely inelastic collision, and kinetic energy is not conserved. So you can clearly see before the kinetic energy was 1/2 m v naught squared, and after it was 1/2 2m, and then v prime squared, but v prime here is just 1/2 v naught. So this just turns into 1/2 times 2m times 1/2 v naught squared. And 1/2 is going to turn into 1/4. And we can clearly see that these two values, this value here and this value here, do not equal each other. So kinetic energy is not conserved in an inelastic collision. These two terms represent the before and after momentum. No, the before and after kinetic energy, and they're not equal, which is yeah, because this is gonna be a 1/4 after it's squared. So these two will not be equal. Do you guys understand how an inelastic collision works? The kinetic energy is not conserved. Just give like a thumbs up if you get it. So elastic collision, everything is conserved. In inelastic collision, only momentum is conserved. And when in an inelastic collision, the objects stick together, it's called perfect inelastic collision. That's correct, yeah. As long as you understand the concepts like Cinchana, you don't need to understand this math here because this math is you have to like remember all these formulas to understand the math here. But as long as you get this what Cinchana said, that's good enough. I think you guys have this, so I'm gonna move on. As long as you like visualize it, you can like figure it out. Okay. Check your understanding. So we don't need to memorize the equations. Okay, so if I already erased it, but like what I before, the only equations I was using was the kinetic energy equation, which is kinetic energy E. I was before to like prove that I was only using kinetic energy is equal to 1/2 mv squared, and momentum before is equal to momentum after, and momentum being equal to mass times velocity, which is all like kind of simple stuff. But if you can't remember it, that's fine as well. But these are the only three equations I used back there. Kinetic energy is equal to 1/2 mv squared. Potential energy, no, I'm sorry. Momentum before is equal to momentum after, and momentum is equal to mass times velocity. Okay, this is a check your understanding. So I'll give you guys like 5 minutes to do these questions here. You can like just DM Jank or me the answers. So I'll be back in 5 minutes. Yeah, good luck, guys. Okay, I got like a lot of answers. So are you guys ready to like go over the answers or should I give you guys a little bit more time? More time? Okay, I'll give you guys like 2 more minutes then. Okay, are you guys ready to go over the answers now? Or do you guys still need more time? Yes, please. Okay. I'm gonna go over the answers now. I got a lot of good correct answers, so good job. Uh, okay, so what principle states that total momentum remains constant in an isolated system? This is just called conservation of momentum, which is like pretty self-explanatory. Uh, because like its momentum is conserved like after a collision or like in anything actually in an isolated system. So first one is conservation of momentum. Okay, what is the unit of momentum? This one can be kind of confusing, but if you think about it, remember momentum is mass times velocity. And we know the unit of mass is kilograms, and the unit of velocity is meters per second. So the unit of momentum is just kilogram times meters per second. This is also technically a Newton second because Newtons are kilogram meters per second. Wait, kilogram meters per second squared, right? Second squared, right? And then, yeah, wait, no, divided by second squared. Kilogram meters over a second squared. And if you just take this times seconds squared up, wait, let me think. Kilograms times meters per second. What is the unit of newtons? Newtons are kilogram meters per second squared. So yeah, uh, wait, this is wrong. Oops. Wait, just forget what I said about this. Okay, kilograms times meters per second. Why do football players follow through when catching a pass? I got a lot of correct answers for this one. It's because they're extending the time of contact, so they decrease the impulse. So like over time, since the force will go down because the time is going up. So overall, this impulse stays the same, but there's less force on like every single instant, so it's easier to catch the pass. And what happens to the momentum when two ice skaters push off from one another? It actually stays the same because this is a like on ice, so we can assume it's a closed system. So the momentum of the two ice skaters will stay equal. Momentum conserve. Wait, let me search up the Newton seconds thing. Yeah, a Newton is a kilogram meter per second squared. And to get that, we just have to multiply. Yeah, this is Newton's times seconds. Because to do that, it becomes times s here. This becomes s squared. Okay, yeah, it's just Newton seconds. So if you ever see Newton seconds, Newtons per second, Newtons times seconds, that's means momentum. Does everyone get this? The answers to these questions? Okay, nice. I'm gonna move on then. You can ignore the Newton seconds part. Just I was just confused for a second. Okay. Okay, so this is a more difficult question. If you guys want, we can go over it together, or I can give you a couple minutes to do this on your own. What do you guys want to do? Should we do it as a group or work on it separately? And then we can regroup. I have one vote for group and one vote for separately. Uh, I'll just let you guys work on it separately for a couple minutes, and then we'll regroup and do it together. If you guys don't know where to start, I can give a couple hints. So I'll draw like a picture first. Okay. So it says object A has twice the mass of object B. So let's call this mass of A is equal to double the mass of B. And it's asking how their speeds compare, but something important to notice is it says they have the same momentum. And remember, momentum is equal to mass times velocity. So that's my hint. I'll come back in 5 minutes and we can work on it. Okay, I got a lot of correct answers, so I'm going to start solving. You guys are good on this question. So, okay. Two objects have the same momentum. We know object A has twice the mass of object B. So if we can solve from what the momentum of each of these objects individually, we can compare them and solve and compare the speeds of each object. So let's say we know these two objects have the same momentum. So the momentum in terms of A is just going to be ma times velocity A, and that's going to be equal to mb times velocity of B. And if we look here, it states in the question that object A has twice the mass of object B. So we have this equation here, and we can just plug this into what we have to get P, oopsies, P is equal to 2mb times VA equals mb times VB. And if we look at this, we can divide both sides by mb, and this will cancel out. So we get 2 times VA equals VB. And looking at the answer choices, they all have VA as its own separate thing on its own side. So just divide both sides by 2. And we get VB over 2 is equal to VA. And that's C. Was that how you guys did it? This is a pretty difficult question. So if you got it, congrats. Does that make sense to everyone? I used logic. Oh, that's nice. You can do that too. Okay. So give a thumbs up or say yes or something if you understand this question. Okay. Okay, I'm gonna move on. This is good stuff, guys. You guys did good on this question. Um, okay, wait. So is it basically for grade? Yes. This is correct. So I got a question asking, so is it basically for A to have the same momentum as to have half as much as B? This is correct, because if you guys remember, momentum is only comprised of mass times velocity, and these two have the same weight in the solving for in the uh like in coming up with momentum. So if one object has twice the mass of object B, if the mass of one thing is double, and if these must be the same, the velocity must be halved. Does that make sense to everyone? Does that make sense to does that answer your question? Thomas is confused. What are you confused about? What are you confused about? D? Why the answer is not D, or I, do you not know why the answer is not D? Yes? Okay. Um, okay, so I'll solve it again. So we know these two objects have the same momentum. So P of object A is going to be equal to P of the momentum of object B. We also know that object A has twice the mass of object B. And we know momentum is mass times velocity. So the mass of object A times the velocity of object A is going to equal the mass of object B times the velocity of object B. Does everyone understand this step here? I'm just setting, it says the objects have the same momentum. I'm just setting object A and object A's and object B's momentum into terms of mass and velocity of each object. Does everyone understand that? Okay, and we also know that object A has twice the mass of object B, and all that means is mass of A is equal to 1/2. Wait, no, sorry. Mass A is equal to double mass B. So if we plug this in, we get 2 mb times velocity of A is equal to mb times velocity of B. And we can see that the masses of B cancel out. So we get 2 velocity of A is equal to velocity of B. And divide both sides by 2, we get velocity of A is equal to velocity of B divided by 2. Does everyone understand that? So that's why our answer is C and not D, because D is 1/4. Okay. You got it now? Okay, nice. If you have any questions, just ask. I'm talking kind of fast, so if you don't understand anything, you can just ask again. Okay. Wait, let me see how many slides we have left. Okay, we have time to do this question. Do you guys want to do this question as a group or individually again? This one is harder. Group. I got one vote for group. I only have one vote though, so if you guys want to do it separately, just say separately. And if not, I guess we can do it as a group. Group. Okay, I have 2 group votes. Okay, I'm just do it as a group then. So a 0.5 kilogram cart moving east at 6.0 meters per second collides head on with a 1.0 kilogram cart moving west at 2.0 meters per second. The carts stick together. So north, east, south, west. 1 kilogram cart moving west at 2 meters per second. The cards stick together. Okay, so when I read the cards stick together, I know this is going to be an inelastic collision, an inelastic collision, inelastic. And do you guys remember what that means? It means that kinetic energy is not conserved. So if any object sticks together, kinetic energy is not conserved. And reading these questions here, that answers number C. It's not conserved. Yes, correct. Only momentum is conserved. Not conserved because it's in elastic collision. So boom, already 1/3 of the way done. Okay, so part A is asking us to calculate the total momentum of the system before the collision. So before the collision, it's just going to be, let's call this, okay, wait, I'm gonna color code this. So a 0.5 kilogram cart moving east at 6 meters per second. This is going to be the blue cart, okay? So this blue cart here is 0.5, half a kilogram, and it's moving east at 6 meters per second. And it's going to collide head on with a red cart. Let's call this the red cart. A 1.0 kilogram cart moving west at 2 meters per second. So this is this red one, which is double the mass. It's 1 full kilogram. And it's moving at a lot slower speed, 2 meters per second. So this is what it's looking like, our situation. And when it's asking for the total momentum of the system before the collision, we can treat these as 2 separate objects and just calculate each momentum separately and then add them together. So this blue one here is going to be mass times velocity, so 0.5 times 6, because this is mass, this is velocity. And then we can add these two together. We add these two together, and then we have 1 times 2 here. So doing this math just gives us, wait, give me 1 second. Okay, so 0.5 times 6 plus 1 times 2. This is just 3 plus 2, and that gives us 5. 5 kilogram meters per second. You guys got that? Yes, 5. Nice. Okay. So determine the velocity of the combined carts after the collision. We know momentum is conserved, so we know, let me scroll here. So we know momentum before is going to equal momentum after. We know this is both just going to equal to 5 kilograms times meters per second because we solved this as the momentum before, right? 5 is the momentum before, it's going to equal the momentum after. So 5 is going to equal the mass after the collision times the velocity after the collision. And we know that since these cards stick together, the mass after the collision is going to equal 1.5 because that's the mass of the two cards together. And then the velocity is what we need to solve for. So overall, our equation looks like this. 5 equals 1.5 times v prime. And solving for v prime here, v prime is equal to 5 divided by 1.5. And I think, let me check what that is. 5 divided by 1.5 divided by 1.5 is going to give us 3.3.3. So 3.3.3 repeating meters per second. Does that make sense to everyone? You guys got that? Does everyone understand that? The equation after 5. Okay, so this equation, we know 5 is the total momentum of the system before the collision, and that just means the momentum because momentum is conserved before and after. So 5 is going to equal the mass of the system times velocity of the system after the collision because these two stick together. So let me draw a picture here. After the collision, the blue ball and the red ball are now sticking together. Oh wait, no, I did this wrong. These two are going in different directions, so there's actually a negative velocity. Wait, let me just redo this. Okay, I'm sorry. These two are actually going in different directions. So is there going to be harder questions? No, there won't be any harder questions after this. So it'll be 0.5 times 6 plus 1 times 0.2. But this is actually going to be negative here. Sorry. It's actually going to be negative here. So the total momentum is actually just going to be 1, uh, 1 traveling this direction in the positive direction. So we know 1 is going to equal P equals the combined mass after the collision times the velocity after the collision. And we know the mass after the collision is 1.5 times the velocity. So our equation is something like this. 1 is equal to 1.5 v prime. So it'll just be 1 over 1.5. And that's going to be 0.666 this direction. So after this collision, these two balls will be traveling together as one in this direction at a velocity of 0.66 meters per second. Does that make sense? Yes. Okay. I'm gonna move on then. Uh, yeah, okay. Oscillations and simple harmonic motion. Is it not conserved in elastic? In an inelastic collision, kinetic energy is not conserved. Only momentum is conserved. Part B is still confusing. Sorry, let me go back. Okay. So we know these two balls, the red ball and the blue ball. After the collision, they're now sticking together, right? They now have a total mass. We're going to treat them as one object now because they're sticking together. So now they have a total mass of 1.5 kilograms because that's just their individual masses added together. You understand that? Mass is now 1.5 kilograms, but it's now traveling at some velocity that we don't know. Okay, we don't know what this new velocity is, but we do know that before the collision, the momentum of the system was 1 kilogram meter per second in the right facing direction. So now one, this is equal to the momentum before the collision, which is also equal to the momentum after the collision. And we know the momentum after the collision is going to be equal to the mass of the two balls together times some mysterious velocity that we don't know. So why is it 1.5? Okay, so we know the red ball weighs 0.5 kilograms. It says right here. And the blue ball weighs 1 kilogram. So we add 1 plus 0.5, we get 1.5 kilograms, and that's how I got 1.5 here for this combined system. Okay. Oh, okay, got it. So here we know 1 is equal to 1.5 times this new velocity, and this is 1 over 1.5 equals 0.66. Oh wait, it's lagging. Okay, wait, it's not letting me draw. Okay, I just equal to 0.666. So what if a patch of magnet was on the red ball and a patch of magnet of metal was on the blue ball and they were facing opposite directions? I don't know. Like, you mean they would like shoot away or like would like are the objects like are the magnets like sided or are they like sticking together? But for some reason these cards are sticking together after the collision. So it's an inelastic collision and kinetic energy is not conserved. That's this question. You guys got that? Put like a thumbs up if you guys understand. Okay. Um, I'm going to move on then. Oscillations and simple harmonic motion. We probably won't be able to have time to go in depth on this because I do have a booklet planned, but I can like just introduce this. Okay. Oscillation. An oscillation is a repeated back and forth motion around an equilibrium position. Some examples of oscillators are like a pendulum, a playground swing, a mass on a spring. Can we just go to the booklet? Um, Okay, well, the booklet is kind of on simple harmonic motion, so I do have to go over that. I'll just go to simple harmonic motion then. Okay. Simple harmonic motion occurs when the restoring force is proportional to displacement and it always points towards equilibrium. So some examples are mass spring systems, a small angle pendulum, a vibrating tuning fork. And okay, do you guys remember Hooke's law? So Hooke's law is just force is equal to negative spring constant times x, where x is displacement. It's kind of hard to imagine, but simple harmonic motion is when like something is moving and the force responsible for moving it is proportional to the displacement and is always pointing back towards some equilibrium. So like on a spring, it'll move up and down, right? Just that's simple harmonic motion. So like simple oscillators will have like simple harmonic motion. Like a pendulum, the force, it's simple harmonic motion because the force is pushing back and it's based on how far up you are. Or like on a spring, on a mass on a spring, the force is based on the displacement, which is based on how far away you are from some point. So that's simple harmonic motion. Oh, simple harmonic motion is only true when the pendulum is like a small enough angle. Because after like some point, um, actually I don't know why. I don't remember why after some point. Let me search that up. I don't remember. Oh wait, it's because of like it's the angle. It's like only the horizontal point of the angle. Okay, whatever. Um, well yeah, they're asking for a summary in chat of simple harmonic motion. Yeah, I think that would be good. And then we could probably just move to the booklet. Yeah, a summary of simple harmonic motion. I feel like we should save the rest for next class. Actually, no, I'll go over oscillations quickly because we still have some time. So an oscillation is repeated back and forth motion around an equilibrium position. So like if you ever heard of like an oscillation, it's just like one period kind of like where like if you're spinning something around, it'd be like one circle. That's what an oscillation is. The equilibrium position is the location where the net force on the object is zero. So like just where it's there's no force pushing on it in any direction. So like on a spring, it's where like it's sitting still. That's the equilibrium position where the spring is not pushing on it or any other force. So the key idea about here is the object moves away from the equilibrium and is pulled back by some restoring force, which is like a spring or like gravity. So that's what the key idea in an oscillation is. So like in an equilibrium position with this swing here, it would just be right here when the child is like when this is vertical, perfectly vertical. Okay, equilibrium. It's where I guess this is where the middle is. It's special and it is basically the position the object wants to return to. It's when net force is equal to zero, and a restoring force is whatever force is pushing the object back towards the equilibrium whenever we move it away. Um, okay, these are just like vocabulary to describe like a wave or like an oscillation. I think we've gone over this before, so I'm just gonna skip this. And okay, simple harmonic motion. We went over this. Hooke's law, force is equal to negative k, which is spring constant, and x is displacement from equilibrium. In this case, the spring is providing the restoring force for these oscillations. Everyone got that? It is confusing. There's a booklet though. Maybe the booklet will help. Uh, okay. I'm gonna start on the booklet now. You can stop recording, Shane.